Great, thank you all for tuning in for my talk, and I'm going to talk about my research called From the Rafael Swell to Mars. So my research is in astrobiology, and if you look at the very broader kind of look at astrobiology, it's more looking towards the stars and looking for a planet that's not too far, not too close from its star. And this is called the habitable zone, the Goldilocks zone, where you have it's kind of orbiting around the star not too far, not too close. It has the right temperatures and the right pressures to create liquid water. However, this is not always the case because if you see, Mars is on the outskirts of the habitable zone, but Earth has life, while Mars on the surface, we don't see the same type of life. So as a geologist, this is not just a question of spatial distribution, this is also a question of time. As we see, Mars today is not necessarily what Mars used to be in the past. So this is a very rough kind of geological scale of both Mars and Earth. So you can see on the bottom it's Earth, and on the top it's Mars. And like the beginning of Mars, you have the Noachian area. So you see it may have had a massive ocean covering half of the planet, while Earth was still a big ball of magma. However, slowly, a lot of its habitable traits, such as a plausible atmosphere, plausible magnetosphere, slowly declined. And as you see around the Hesperian, you start having these pots of water that are isolated, and it's probably lost a lot of its atmosphere and magnetosphere. But in Earth, you start seeing the first kind of microfossils. So we know around that time, Earth was habitable already. So it's really interesting. You could see this kind of inverse kind of relationship where Earth is today full of continents and life and water, while Mars today in the Amazonian is more of a desert. So I'm looking at the kind of the Hesperian time. So you could see these valleys, you could see these areas where we think there could have been pots of water. And you also see a lot of this white type of mineral, a lot of calcium sulfate that we know on Earth today can be used to support microbial communities. And we're trying to kind of use this as an analog to understand what may have happened on Mars at some point, and could this ever have supported life? So this takes me to my research site. So first of all, I'm showing you the top image is the veins from Garden City in Mars Sharp on Mars. And you see these veins, they're calcium sulfates. Again, and from the bottom image, you could see the veins in the Carmel Formation on Utah, which is my research area. So you could see just from the morphology and just from not really knowing the area or the geology too much, it's similar in the morphology. You also see the veins that are relatively similar, and they're both calcium sulfate veins. So as a geologist, I first want to go back in time to understand really what's happening in my sediments. So you could see it's in Utah, USA, in the Colorado Plateau, and the San Rafael Swell. And you could see the red dot, it's exactly where my research site. And then on the left, you could see kind of a sketch I made to just represent what happened during the Jurassic 166 million years ago when my sediments were deposited. So they were deposited underneath the Sundance Sea. But as the Sundance Sea regressed, it left pots of water. These pots of water slowly evaporated, creating a thick layer of salt called sapka. Now these sapkas are mostly calcium sulfate. Later on, around 40 million years ago, as the San Rafael Swell formed, these sapkas were remobilized into veins, into the sediment, as you could see from the image and the sketch, and you created these veins of calcium sulfate. Again, very similar to what you see in Gale Crater and Endeavour Crater on Mars, both images on the bottom. Later on, around 4.6 billion years ago, you had magmatic intrusions, vertical magmatic intrusions that entered these sediments. So you could see on the left, you could see a real image, and the kind of the dark gray thing in the middle, that's the magmatic intrusion. And that's a sketch on the side. There I have Austin Dike and Baby Dike, because a magmatic intrusion that it's intruding that way is a dike. It's called a dike in geological terms. Now this environment can create a habitable environment because it creates a heat. It creates heat, and that heat can remobilize and change the chemistry from the crystals and create possibly a fluid that possibly can support life. So just to kind of show you, I made a video how this will actually happen in live. So this would be a magmatic body if you think about the magma chamber, but then it kind of intrudes inside to the sediment. So this is an example of, you have the sediments, which are kind of the red soil, kind of more similar to Mars and my research site. And then you have the veins representing the gypsum. But you could see it's really hot. So that wouldn't be habitable because it's 120 degrees, and we only need habitability, as we know on Earth today, is up to 121, 22. But you can see it's slowly cooling, and also when it cools, it has different alteration zones. So you have really hard, maybe in the middle where it's thinner, but inside it can still be hot. And just beside the dike, the intrusion, you could have an alteration zone that really is altered. You have a lot of mobility of minerals. And as you go further away, there is no change at all and no effect on the rock. So what I'm actually doing is, this is an example of calcium sulfate vein from my site. And then I make syn section out of it. This kind of rainbow color is a syn section under cross-polarized light. And then I put it underneath a scanning electron microscope. So what is a scanning electron microscope? If you see, for example, the nucleus here, it's, for example, an atom of, let's say, aluminium, and you bombard it with electrons. And as you bombard it with electrons, the electron of the element pops out and releases a characteristic X-ray photon. This characteristic X-ray photon is characteristics for each element, and then you can get a map of the element distribution. So here's an example of an unaltered rock further away from my dike, and you can see two images here. Here is the electron image, but also the chemical image. So you could see all the different colors represent different chemistries. And we could start building a kind of an image of what was there, what formed during the Sundance Sea. And then what I'm going to do, I'm going to look at the alteration zone. So this is an example of free samples from nearest to the dike, slightly furthest away to the dike. And then I put that under SEM as well, scanning electron microscopy. And you, just like that, you could start seeing there's different morphology, there's different chemistry, the different colors are showing us something else. However, just based on the chemistry, I cannot tell what minerals are there because same minerals can have the same chemistry. So I'm going to combine that with Raman. What Raman does, it sends a laser which detects the vibration of the molecule and has a Raman scatter. And the vibration of the molecule will tell us the structure of the mineral. So then you can combine the chemistry with the Raman. What's really interesting about this is at the moment we have Perseverance, a rover that's sent to Mars at the moment, and it's hopefully going to land around February. It has a Raman, it's called SHERLOCS, on top of it, and it's going to detect similar thing. It's going to detect in a similar way. So then my data can then be compared directly to data coming directly from Mars. So what am I actually going to do with all this data eventually? I'm going to do a geochemical model, all computerized. This is just a sketch to illustrate what I'm actually going to do to make it kind of easier to imagine. So I'm going to look at different water to rock ratios and change different parameters such as temperature and gases and different stuff to try to understand what kind of fluids formed in this reaction. Then I'm going to prepare these fluids in the lab conditions and detect different microbes that may be able to survive in that environment. Finally, I'm going to evaporate this and create a layer of salt. This layer of salt will have some fluids in the pore space, but that can give us possibly an indication if life ever evolved on Mars, could it have survived till modern time within crystals? Because we know that today on the surface of Mars, life cannot survive due to radiation. So in conclusion, I'm looking at magmatic intrusions into sulfate-rich sediments from the San Rafael Swell on Earth. I'm reconstructing the past environments by geochemical modeling, testing whether it can support life as we know it, and then testing if it's possible planetary habitability. Thank you very much all for listening in, and take any questions.